Big new idea from yesterday. Coefficient ratios, also known as mole ratios, or just the connector, which is coming from the balanced chemical equation, are ratios that exist. Okay, so we're still using our ratios. We are still using our grams per mole within molar mass. We're still using the liters per mole, which is the 22.4 liters regarding volume. And we're still using Avogadro's number per mole. Those are all conversion factors we are just awesome at because we've been using them for a month.
Teachers, please.
Go.
Excuse.
See you in a minute.
AP students, last names beginning H through N at this time to the cafeteria for the bubbling session. Again, AP students, last names beginning
You are an AP student, H through N. Please get out of the room.
Cafeteria this time.
Hurry back. Okay. So the only other conversion factor that we have not learned, okay, I say only, but the one that's relevant for us today that we've not learned is called molarity. Molarity, what's it called? Molarity is represented by capital M, and you've actually seen these in the lab already. So you maybe have seen a solution, and on the label it was some concentration, and you're I don't care what the concentration is because it didn't matter at that time, but now it does. So if I say 2 molar, that's called 2 molar sodium hydroxide. What that means to you is that the ratio within that, the mixture is composed of 2 moles of sodium hydroxide in 1 liter. So I can write it like this. I can say 2 moles NaOH per 1 liter of solution. And that to you is a fraction, right? And you can flip fractions. If you want to, you can flip that fraction based on how you needed to utilize that in the conversion process. So remember, any conversion factor is flippable. It's based on how you need to cancel units. Okay, so we're going to use that in this following question. And this is a third lecture example that we didn't get to yesterday. Okay. So you guys will do the first step for me. What's that first step? Writing out what? The equation, right? Write out the balanced chemical equation. Courtney, come sit over here. This first front table, or that one back, and those two at least okay. This is a part single. Oh, and if you don't have a calculator, grab a calculator. Just saying. And let's assume this reaction occurs. I did not provide you an activity series. I'm sorry. Let's assume it is going to occur. I'm not going to give you a no reaction on this one. Bryce, you can bring that whole calculator box with you. Since you're popular. All right, so get me started, Riley. Keep going. Okay, so you're looking to replace 2 metals, right? So I'm telling you magnesium is more active, so it definitely will replace. So copper gets booted out, and who does magnesium go with? And how does that form? What's the formula? MgCl2. So you're crisscrossing your charges, right? Crisscross charges, so you don't forget to do that. And then when you balance it, what do we need, guys? 2 where? Copper 1 chloride and on the copper. And I think we're good. Okay, great. So here's our single replacement reaction. Now, you guys did a lab like this, where you had a solid, like the solid piece of silver, and you added we're going to make this happen. Okay. Okay. Now let's go. Okay. So we had a solid piece of metal. We added a solution. So like the copper 2 sulfate was the one you guys used, and you just put a dot or a drop of it on there. So this is an aqueous solution technically. And of course copper would be a what? Solid, and this would be the solution that's formed once the replacement had occurred. So this would be aqueous. So we have to have solutions present, like liquid volumes present. And that's when we start to see this M. What's M called again? Molarity, because it's trying to indicate to you the concentration of that solution. So like, for example, if you had a really concentrated Kool-Aid, it would be like sludge, but it would be a high concentration, so it would have a high molarity. Is that a high molarity? No, that would be like really, really crappy Kool-Aid. That's really dilute. That's not very good. So we would never drink this, by the way, but I'm just saying it's analogous. So that's why you're trying to see these M's, because we have solutions present. Okay, so now we have volume. Notice this is volume of a solution, so we shall not think of what? We have volume of a gas, and we have volume solution. So when you think volume of gas, what number comes to mind? 22.4 liters per mole. Of the gas, we cannot use that here because this is solution stuff. That's why we cannot use it. That's why we have to use molarity instead. All right, and then how much copper will precipitate out? When I say much, what does that generally mean? Mass. So our question is grams of copper will precipitate out. So we kind of see that from the equation. And then this information collectively together is the given. So the way you use this together, because it looks like there's two numbers provided here, like which one do I use? You actually use them both. This is how you approach it. The given, you have to somehow get to moles. So you're going to do M, so capital M is molarity, times V, volume, and that's going to give you moles every single time. Okay, so what's capital M in this case? So what's the number? 0.40, and break that up. So that molarity, I don't want it as capital M anymore. What were the two pieces, the numerator and denominator? You just wrote this down for warm-up. So that many moles, and who's the solute this is speaking of? Copper 1 chloride. Okay, so that's the moles in 1 liter of solution. Okay. But we don't have a full liter of solution. We only have how much of the solution? 500 milliliters, right? So I see milliliters, but I see liters. Those don't match for me. So can you guys convert that to liters in your head? It's half a liter, right? Because 1,000 milliliters is what a liter is worth, so it's half a milliliter. So we're going to multiply that by 0.5 liters. So M times V. M is broken into the 2 units. You can see them better. And multiply by V, which is volume in liter form, and what cancels? Liter cancels, and we get, you guys do that in your head? What's 40% of 0.5? 0.2, thank you. So that's 0.2, and what units remaining? Mole. I'm going to put 0.20 because this actually had, see all those sig figs there? 0, 0, 0. There are a lot of sig figs there. 1 second. Okay. So this is 0.20 moles copper 1 chloride. That is not our final answer, but that is a good place to stop for a moment. Yes, sir.
What did the 0.5?
It came from this volume right here, but we converted that in our head to liters so we can cancel those units out. Okay. All right. So now we're in moles of copper 1 chloride. Can you guys get to grams of copper? Totally. Go. You got that. I just had to get you started using the molarity piece so you can figure out how to use your mole math now. You probably need your table out so you can grab that molar mass. All right, what's your first step in this conversion, guys? Moles to what? Moles of copper 1 chloride to, say again? So our goal is to get from copper 1 chloride to straight copper, right? Here's copper 1 chloride right here, and here's straight copper. So you have to jump from mole to mole, right? You have to use the mole ratio first. So what's going here?
On the bottom is 2 mole copper chloride.
2 moles of copper, 1 chloride, according to the balanced chemical equation. What goes up here?
2 moles of copper.
2 moles of copper, according to the relationship in the recipe up here. So we've made it a copper score, but we have not made it grams of copper. So what's that last step?
1 mole of copper.
1 mole of copper weighs
63
grams of copper. Good. All right, and then what's that final mass?
12.7.
12.7. I think I need 2 sig figs, so 13.
Yeah.
Okay, so 13 grams of copper. That's a lot of copper. And this is actually how I make copper sometimes in AP Chem when I need copper and I just need some particulated copper. And I'll just do the same replacement reaction, filtrate the copper out, boom, we have copper to use. So that's a significant amount. 13 grams is a good amount. All right, so molarity was the only weird thing on that question. I'm going to do another molarity question in a couple minutes, but I think you guys can do B and C of this particular question on your own. Talk in your groups as you go. Again, you have a copy of this, so just FYI. There's the whole back seat, basically. So if you want, what's the molar mass of copper 1 chloride? What is it? 90? 99? 99 point.
99.
It's 99, okay. I was like, I know it's not 99. Ooh. Does anybody realize the typo in this question?
I noticed it.
What is it?
It's because copper chloride, it says formed, but it's actually one of the reactants.
Okay, that's not what I was looking for. Dang it. Reacted. Okay, there's another one. Anybody? It says molecules, but it means atoms. I like to change up my reactions and not actually change the verbiage, as you can see here. And we can do this in our head, right, guys? So 102 divided by 99 is about 1. Divided by 2 is about 0.5. So half is 6.02. It's around 3 times 10 to 23. 101? Yeah. So, yeah, I need all that, don't I? All right, keep it rolling. That last piece done, if you are ready. And if you are willing, you can go on to student practice number 4. I think that's it. Yeah, student practice 4, then you try 4. Yeah. Nation is home. Then who's about 4? 4.13. 4.13. You do about 30, like that's about 33, right? So it's about a third of 24 is what? 8 divided by 2 is 4. It's a little higher there. So you guys can technically do that. Estimation. We have to do that a lot in AP Chem because they don't have a calculator on the multiple choice test exams and everything. So. Alrighty. Finish that one. And we are going to use our computer shortly. So I wonder if they're charged up. We'll finish this next question, then we'll go grab those, okay? So I just want to practice one more with molarity so you're comfortable with it. So kind of doing around 2 of each style of question. Are you guys feeling okay with what we've done so far?
Yeah.
Okay, what's molarity one more time, units-wise? Moles solute over liters of solution. And if I'm giving you a volume and a molarity, how do you combine those to get to moles? And the volume must be in what unit? Liters, for the liters to cancel. Good. All right, so student practice 4 is next. Oh, we don't know exothermic credits yet, so that's not a good quiz, a good joke. All right, so sodium sulfate, barium nitrate, ready? What's sodium sulfate? Close.
No, Na2.
Na2SO4, right? Sodium's a 1+, sulfate's a 2-. Barium nitrate, somebody else? Come on, let's go, Bailey. BA. N. Parentheses. Nope. Good. So barium's a 2+, nitrate's a 1-. Everybody, what kind of reaction is that? Double replacement. So give me the double replacement. Corbin's table. Give me one of the products.
Na2, no, Na. Nitrate.
No choose. So sodium is a charge of what?
2, no, 1.
1. Nitrate is a charge of
And then 1.
1. So we're good there. And then front table up here, give me the other product. Good. BA. What's the charge of barium? What's the charge of sulfate? 2. So in the end, we wash them out. All right, okay. So here we go. We got a reaction with sodium sulfate and barium nitrate. This is not balanced. What do I need? What do I need? A 2 where? Only good on the sodium nitrate. Okay. So reading the first question, if 120 mils of a 0.01 molar solution of sodium sulfate reacts completely, how many grams of the precipitate will form? Okay, so if you hear the word precipitate, what do you need to ask me for? The arrows thing is the activity rules. Solubility rules, right. So, and I'm just going to throw them at you. Catch them. Alright, figure out who your precipitate is first. Did you not? I have some that are a little bit yellow. Regardless, you have the solubility rules in front of you. You can do it. Let's go. Where's the precipitate? Who's the precipitate? Say again? Why barium sulfate? Good. So all sulfates are soluble except for barium, calcium, and strontium. Right? Is that what it says on the sheet? Or barium.
No, mercury,
Oh, sorry. So strontium, barium, mercury, and lead. Okay. So we've got sulfates all soluble. This one is not one of those, so we're going to put a precipitate here. So I'm just going to put it as a downward facing arrow to indicate precipitate. What's the rule for all nitrates? No problems, right? Always aqueous. So I'll put an AQ there to indicate that we've actually identified that solubility. All right. So these are two solutions because it doesn't indicate anything else. So unless I tell you something else, there are solutions of the two reactants here. So you can see that the solution information is starting to be given, therefore we're using molarity. What are the givens we must combine? Okay, so the 120 milliliters, I don't like that milliliters look, so can we change that? How many liters is that? 0.12, right? So we're going to back that thing up 3 times. We get that divided by 1,000 to give you liters. So I'm going to do M times V again to get to moles. M times V gives us moles. So M is 0.101 or 010 moles of sodium sulfate per 1 liter of solution. How many liters of solution again? 0.1200 liters. And so the liters will cancel out here. And we get to moles. You know what? Do I have to stop? Like, do I have to stop my process and, like, reset? Or can I just keep rolling?
keep rolling.
Technically, I can keep rolling. Like, I can stop if that makes you feel better. We get moles, and then you're like, okay, I'm going to stop with moles of sodium sulfate, and then kind of keep going through my mole math. But technically, I should be able to see that I'm in moles of sodium nitrate, or sodium sulfate. And what was my question here? Grams of, who's the precipitate? Barium sulfate. So technically I have moles here. I know this looks weird because it's next door, but we can technically cancel moles next. So if I made this look like normal, we can keep on rolling. So I have moles of sodium sulfate I need to cancel, right? Who do I want to get to? Well, give me baby steps, right? I'm in moles of sodium sulfate. What will be my next logical step? Barium sulfate moles, right? I'm in the middle of the mole map. I'm technically at moles of sodium sulfate. I need to get to moles of the other guy. So I'm going to go mole to mole. So what am I looking for? The ratio. What's the ratio? Right, it's 1 to 1. And I know that you're like, it doesn't change my math. It doesn't technically, but it does change the process. So we're going to put 1 mole of sodium sulfate on bottom and 1 mole of barium sulfate up top. So that recognizes our transition from the sodium to the barium. Now we're close. What's my last step? Convert to grams of, yeah. So I'm getting to my final answer because technically the moles of sodium sulfate cancel here, and my moles of barium sulfate are what I need to convert. That's the only unit remaining. So 1 mole of barium sulfate, anybody got that molar mass? 137.73 plus 32.06 plus 64. What is that? That sounds great. 233.34. Okay. This one's a little bit more challenging, but we could do it. 0.2528. Can I get one more? Or no, that's good. 260 grams of barium sulfate. Again, the only new thing is what in this case? Molarity. And I just wanted to show you that you didn't have to stop. If it makes sense to you to stop at moles of sodium sulfate and go, okay, how do I want to approach it? You could totally take a breath and move on. I just want to show you could just do the whole shebang together. And if it makes you feel better, you can put the volume up front so there's not this weird gap in the middle. But it's just unit cancellation. So cancel your liters, cancel your moles of sodium sulfate, cancel your moles of barium sulfate, and leave it yourself with grams. All right, let's just do B, and then I think we don't need to do the rest of this technically. All right, I like B because it changes it up a little bit on you, okay? I want you to read and think about how you want to get started, and notice that this last thing provided to you is going to be held last, okay? So I'll tell you how to use it last. Give me a thumbs up if you've made it to this point and you've made it to full. Very nice. Okay. Think about how you can utilize that molarity and cancel out moles. Alright, so if you're looking at this right, your moles of sodium sulfate are gone, your liters of solution are gone, you have moles of barium nitrate. What is this question referring to? What's it asking for? Right, milliliters. Well, that just technically means volume, right? It's looking for the volume of the barium nitrate solution. So liters is fine, and we can later on convert that to milliliters. So how could I utilize this to get what I want? Flip it, right? It's moles per liter, right? That's not going to work for me if I put moles per liter here because the moles will be on top, and it's not going to cancel. So if I flip this, this is technically 0.01 moles of barium nitrate per 1 liter of solution. So if I flip it, I can keep the numbers and the symbols kind of where they belong, and I just invert it technically. It'd be 1 liter solution on top, 0.010 moles barium nitrate on bottom. What happens with moles of barium nitrate? here, here, right? They cancel, which is our end goal, and we get the liters of solution. So once I get the liters, I can totally get some milliliters if I need to. So let's just solve for liters first.
Don't you need to put liters on the bottom so you can convert it to milliliters?
Well, so the next step, I can convert it from liters to milliliters. I was just letting people pause and go ahead and solve for liters if they wanted to, because that would, like, you could actually see the milliliters even from the decimal version of that. So what's 0.005 times 2 is 0.01. So is it 10? No. 0.0, what is it? 0.0?
It's 0.001.
0.001? What's up?
You have 2 moles of barium nitrate.
Hi.
Are you sure it's 2?
No, it's not you. Thank you. I was scrolling up and down. Thank you. This is a 1 mole of barium nitrate. Okay, so it's 0.05. Answer is 0.05 liters. Yes? Because that number and that number are the same. So the only thing left is this number, and everything else is 1. So 0.05 liters of solution. How many milliliters is that? 50. And you could do that in your head or show the process of converting that. Okay, there's our final answer. I wanted to do this one because you simply, just understanding that this is a conversion factor will open many avenues. Understanding that conversion factor can be flipped. It'll be applied here should give us the correct answer. Yeah.
Couldn't we have just seen that the molarity was the same?
If you were smart enough to do that up front, but then I don't know how you show you that work for me. But yeah. Yeah, if you're understanding like the conceptual idea of how things combine in a 1-to-1 mole ratio, you could totally get that. Yep. Okay, let's go ahead and go laptop. Your laptop, preferably. We're just going to get it booted. All right, while this baby's logging in, please go ahead and write down what's on the board. Unfortunately, the first half of the series, Enlo talks a lot, a couple days. Unfortunately, I'm talking a lot for the next day and a half. While your computer's booting up, please. So we kind of did reactions, and then we did reaction stoichiometry, and that reaction stoichiometry process is just converting. It'll apply to real life here towards the end of the week. Right now we're just mastering the skills of stoichiometry. This percent yield sounds like kind of a separate topic, but it applies to all of our reactions and all of our reaction stoichiometry. So we have to just understand how to identify what yield is, and how can we see how good our yield is, like how good was our reaction. And we're going to use some of the terminology, as you see here, to help describe that. Does anybody recognize these terms? Where did you see them?
The reading guide.
Yeah, there were the two that, like, basically only two definitions in the reading guide. And they make sense. So if we're having a reaction happen, let's say you're baking 2 dozen cupcakes. In our reaction, we kind of know one of those reactions that talk about the baking soda rising. But we have 24 we want to make. Let's say 2 just burn up and just totally smoke up the kitchen. 1 the dog ate, fell off counter, and the other one you just had to try it to, of course, make sure it was quality goods. So we lost 2 to burning, 1 the dog ate, 1 you had to eat. How many do you have left? 20, right? You made 2 dozen, 24, 4 got lost, you have 20. How's your yield? You made 20 out of 24. How's your yield? It's all right. Like, you know, you lost 4, but you didn't lose like half of them. So it's probably up in the 80%. What's 20 over 24?
So about like
85? 83%? Like 83% yield. That's a pretty good yield. But like if 20 of them caught fire and you were left with 4, you'd be making some more. Your yield will be crap. Your yield will be very low. So this is all it's talking about. Your theoretical yield, as the recipe says, you can make 24. Theoretically, in La La Land, if nothing went wrong, everything was perfect and there were no dogs around and you didn't have to try one, your theoretical yield would be how many you made. And that's a La La Land yield. Nothing is ever perfect, especially in our labs. I'm not saying you guys aren't skilled. I'm just saying that sometimes things get washed down the drain when they're not to, or somebody spills something, or we don't correctly measure that meniscus. So the theoretical yield is really like La La Land. Okay, and it's gonna just not occur because we're not perfect human beings. Okay, but it is a theoretical possible amount that you can make. In a question, this would be calculated in a problem. You would have to calculate this in a problem, or like on a recipe, it would be given to you like theoretical yield is 24 cupcakes or whatever that may be. So actual yield is what you actually physically get at the end. So first example, physically got 20 cupcakes. In your lab, maybe you got 20 grams when you should have had 25 grams at the end. So this is your actual yield. This is what you get in the lab. And it would be like measured. Just so you know the differences of how those would be delivered to you in a problem or in a lab situation. And so this is what you get, okay? And so how do you think we're getting percent from this? But what are we multiplying by 100? Dividing which ones? Dividing actual, what you actually got, by what you should have had, and then multiplying that, how did I get there? By 100. Actual yield over theoretical yield times 100. Okay? Actual yield over theoretical yield times 100. And that would give you your percent yield. What would be a really good yield? What would mean like you are a super awesome lab partner? Okay, you're probably not going to get 100 just because the contamination. 99 would be wonderful, but what would be acceptable?
96.
96? You guys are harsh. I was going to say like 80% yield is pretty good. In like college labs, they're like crossing their fingers for like 50% yield. Okay, because sometimes the experiments can be quite taxing or quite technical, and so things just don't work out. But if you get like 20% yield, I'm kicking you out of my lab group, right? So there are some yields that are really desirable, some that are not so, that just don't work so well. So that's how we get our percent. And this is my favorite from a Bossa Purifying, 9.6% yield. It's sad. He thinks he's good and he's not. I thought that was a sad story. And then there's a lab we do and we have like a 3-day lab in AP Chems towards the beginning of the year. So if you know anybody there, ask them about it. And the idea is that you get wonderful percent yield, like 90s, 80s, and 90s. And lab-based or lab grade based on percent yield, spend an hour pathetically scraping every last gram of product out of the glassware table on the floor, because when you spill it, you're like, no, I lost all my percent yield. So that's happened many times, many times in my class. You guys can ask them. Okay, so let's do this one problem with this. Okay, it's on you. I think you can do this. Write down the given that you can start with. Think about maybe what you need to find to get percent yield. going. Not a lot of this. Okay, let's dissect this. I'm not problem solving. I'm just dissecting. Okay. All right. So we know the question is percent yield, right? What does that mean? I need an actual yield. I need a theoretical yield. I'm gonna multiply that by 100, and that's gonna give me my percent yield. Which of these do I already have? Why would I have to give you guys the actual yield for this problem? You're not in the experiment going back there doing the lab. We're not going to stop right now and go do this. We want to know what the actual yield is. So I have to be providing that to you in the problem, or we measure it in the lab. So what is the actual yield? How much? 3 liters of the gas, right? We'd have to do the reaction to figure out this gas is. So this is the actual yield. So I might just put AY equals 3 liters, make like a little list of givens over here. Okay, so we know that. So what are we technically having to find? Theoretical yield, right? So our question is, what's the theoretical yield of said gas? Right? So that's what we have to find. And that's going to be in liters. I didn't mention this earlier. Anytime you do percent, it has to be the same unit on top and bottom or they won't cancel, right? So that kind of makes sense. So it has to be in liters. What do we also know? Okay, and what's happening to magnesium chloride? It's decomposing. So what do you think we should do with that information? Make an equation, because if not, we're stuck. We can't do nothing. Because we don't even know what gas is being made, much less calculate with it. So taking this information, we know what's the formula for magnesium chlorate? MgCl3, ClO3, 2. Okay, and we know it's going to decompose. Okay, so we know that. We know that we have 14 grams of this. All right, now we're cooking. So we're going to take some information, and let's go ahead and find what the gas is. Anybody remember how a chloride decomposes? Metal chloride and oxygen. So now we know the gas, right? So we still need to balance this. Mg Cl2, right? Crisscrossing charges. And oxygen. Balance this. 3 on the O2, and it's good, right? All right, so now it's balanced. Now we have the gas. So this gas is oxygen. Now we know that's oxygen. All right, where do I start to end up getting theoretical yield of liters of oxygen? I have to start with what? 14 grams. That is the only given provided. I have to use it. Okay, I'm going to squeeze this in here. I have grams. Grams is only connected to one thing on the mole map. What is it? Moles, right? So I'm going to convert 2 moles of magnesium chlorate. Wait, I'll wait on you human calculators. 24.31 plus 2 times 35.45 plus 6 times 16.
127.
Is that right? I get a second on that. I'm hoping it's right. I've already written it. Is it good? Better be right. Okay. All right. So we have. Can someone double check? Okay, I thought that was a little low, but usually he's decent. So 191.21. Okay, here we go. We're back together. This is why we have to have human calculators. All right, so we made it to moles of magnesium chlorate. You guys get to liters of oxygen. Go. You're getting to liters of oxygen. I believe in you. No. Is it around 7? 4? You off, okay. 4.92 liters of oxygen. Okay, what kind of yield is this one in red? What yield? Theoretically. So like in La La Land, or La La Land, however you want to say that. In La La Land, if you took 14 grams of magnesium chlorate and you were like, okay, decompose, magically decomposes and makes oxygen. In a perfect world, you would make about 5 liters of that substance, of that gas. But we, us lowly humans, only made how much? We only made 3 liters, right? So if I'm approximating, I should get about 5. I only made 3. What's about my percent yield? What's up? I don't know why I did grams. It's a habit. So that's actually not, that's why I estimated a 4. I mean a 7. No. This is right. This is from memory.
That's right.
This is right. It's 22.4 liters. I'm going to just say, I'm hoping this is just a phase that I'm in right now. Okay. But regardless, this is theoretical yield. What's approximately the percent yield? It's about 60, like 3 over 5 is about 60, but you're definitely going to calculate it now. 3.00 liters of oxygen divided by 4.92 liters of oxygen times 100, what is it exactly? 61% yield, okay. Would you want this person in your lab group?
No.
No, but would you settle if you had to? Yes, okay. All right, so my people who just came in, they're going to explain to you molarity and the percent yield aspect. I'm going to give you guys about 5 to 10 minutes. Walk them through examples 3, 4, and percent yield. Buddy up.
So, what do we want?
You're walking them through everything we've done. They basically missed all of it.
So when you're given a molarity, the symbol's just like a capital M. You multiply the molarity by the volume, but the volume has to be in liters. So like on those ones, it's giving us milliliters, we have to convert it to liters, so that way we can do that. And so that will give you like your actual amount. And that's the only difference of what you actually have to do. And then for this one, this is percent yield. So to calculate percent yield, you need the actual yield.
Hold up. I'm going to suggest that you sit at his lab station with the people that just came in, just so you can spread out and actually talk. Okay, so I've got Chris, I need somebody.
I don't care, we can go grab my percent yield.
We put it over 1. Well, that was just like what we read. Or we might have just I'm trying to find because you look at this start with A on practice. Whenever you take molarity, it's based on like volume or it'll say something like this amount, this molarity solution. So this is the next part. Not amount, but that amount that you have the volume. So you use that over one over solution. You find the logic and sometimes like the leader and that's how you like say there's like a 65 milliliter solution of or there's 65 milliliters of a 0.005.
It's going to give you the molarity, which is the
0.05.
So what you're going to do is you're going to use a source over 1 liter solution. So
Give me something.
it's going to be on this one. It's going to be 1 liter multiply that by oh yeah, it's the liters of 5.3. So the number of 0.05 divided by 1 liter, so I
So that's what
and then so when you do that here, how it goes.
and then like say you needed like a brand or like one of those things you just
So I don't know why we do it.
the percent you get what's on the rate, the percent you is just actually
Then you're going to do the moles of what you're converting
the
to.
definition is pretty straightforward. Actual yield. Yield is like what's
Alright guys, after you feel like you've explained, have them regurgitate, have them talk back to you on like what the whole process entails, how to calculate, and so forth. Let them see your notes, don't just talk at them.
Because that's what
Okay, so it's the
you're trying to get, it says how many grams of this
I just wrote like this one, this is like
you still have to go ahead and try it. And then
basically like with the convection points I think in that moment I was talking about
Yeah.
And so I think that,
Wait, was that this?
just for that one, what you
All right, so my people who just came back from AP bubbling, I'm sorry, they did not tell us today until today. So I had to do what I had to do. So you have a little bit of a background. You also have the ability to go back and watch the piece of the video that you may need to. We're going to do one last topic today, and it's applying the same concepts, it's just in a different way. Joke for you first. What is a chemist's favorite plant? Say again? I'm hoping that's right. No, stoichiometry. Or chemistry. Close. Okay. Done. 2 strikes today. 2 strikes. Okay. We're going to talk about this, but we're going to talk about it in a simulation. So go to Gizmos, which is at explorelearning.com, which is why you have your laptops now. Explorelearning.com. Monday.org. Nope, .com. There we go. Don't judge me on my tab situation. And when you get logged in, you'll go to your assignments. I can't remember how that looks on your name. No, it'll be called limiting reactants, as it states on the board. You actually have to download the worksheet. I think you guys have the ability to download the worksheet, am I right? It says student exploration sheet. So you have to download your own student exploration sheet, which I think is below the little C layer. So it pulls up like this, and then it says student exploration sheet right here. Help a brother out at your table if they don't know where they're going. So I would encourage you to find a partner to hold up the simulator, and then one person will pull up the worksheet, and you can work with them, but you need to write this in your notes or on your own paper.
Well, I'm logged in. Okay. Yeah, I thought so.
I'm going to give you the class enrollment code, okay? All right, so can you do make an account, and then that's the class enrollment code? Let me know if that's working. All right. Alright, if you need help someplace, let me know.
You got it. You got it.
Let me see if I can do that.
What is something here? Whoa.